Thanks, Satya. So I know probably you're spoiled by the other program where they introduce you, with all, pearls and so on. Now in this program we don't. So you have to introduce yourself and then tell us besides what you're thinking about. Okay, thanks anyway.
Okay, so my name is Satya Majumdar. I'm from University Saclay, and thanks Luca for the invitation to this workshop, and also thanks to the other organizers of the other, because I'm participating in both the workshops, Tani and other people. And so I'm going to talk about the convex hulls of two-dimensional stochastic processes. This is a subject that we have been working for the last 15 years or so. And so what I'll do is, in the beginning, I want to just develop the formalism, how to sort of attack these problems, and tell you the motivation which comes from the animal movements and so on. And only at the very the second half of the talk, I'll come to more recent stuff. So in the beginning, I'll just talk about the little bit older stuff. So some of you might have heard already. So, but hopefully it will be interesting. All right. So here's the sort of the plan of my talk. So I'll start by reminding you what is a convex hull and what is a random convex hull, and then I'll talk about two processes. So one is just a simple random walk or Brownian motion, if you like, and the other is a branching Brownian motion or branching random walk. So the second one is related to Fisher equation and so on. And then, as I said, the motivation comes from an ecological problem and animal epidemics. So I'll talk about that. And then I want to show you some very, very interesting formula due to Cauchy, which is not so well known, about the perimeter and the area of a closed convex curve in 2 dimensions. And using that, we'll be able to sort of compute a few things exactly analytically. And then it turns out that this is a very general formalism to calculate the perimeter and area of convex hulls of several 2D stochastic processes. And I'll give you some examples. So this will sort of tie up with the other conference. There'll be active particles here and run-and-tumble particles. And finally, I'll just summarize and conclude. So let's see how we go. So let me start with convex hull. So many people know about convex hull, but let me just remind you. So let's imagine that I give you a set of points like here or like this, and ask you, what is the shape of this set of points? Now, this is a very ill-defined question. Like, what do you mean by shape? But nevertheless, when you look at this, you will tell me roughly that this looks like a triangle and this looks like a square. Now, when you are telling me that this looks like a triangle or this looks like a square, your eye is actually doing an experiment. Basically, what it is trying, it's trying to draw the contour around this set of points, kind of tightest contour or polygon, if you like. And that polygon has a shape of a triangle. And similarly here, that polygon has a shape, the sort of closest contour that you can encloses all the points, convex polygon. So that is the square. Okay. So convex hull is precisely that. So here is the Wikipedia definition of convex hull. Imagine that you have these nails on a wall, and just in there, and you take an elastic or rubber band and you stretch it outside, enclosing all the points, and let it go. And then it will shrink, and then at some point it cannot shrink anymore, so you get stuck. And so this is the sort of minimal convex polygon that encloses all the points. So that's the convex hull. Okay. So why is it called convex? Because just to remind you, so if I have a closed curve like this, a convex curve means that if I take any 2 points and draw a chord on it, then all the points of the chord lie within this curve. Okay? So this is a convex, this is a convex, but this is a non-convex, because if I just join these two, some points are outside the curve. Okay? So that's why it's called, I'm going to focus on the convex hull, basically. So now here's the sort of general setting of the problem. So imagine that we have a set of points in 2 dimensions. So you can draw there's a unique convex hull given this set of points, okay, which is this minimum convex polygon enclosing this set. Now, if I change these points and draw another set of points, then the convex hull will change and it will have a different shape. Okay? So the shape of the convex hull is, different for different samples of these points. And so the very general problem is the following, that imagine that I give you now a random set of points, R1, with positions R1, R2, R3, Rn, and it's drawn from some joint distribution. Okay? It can be independent points, in which case this will factorize, or it can be correlated when it doesn't factorize. So you give me this joint distribution of the set of points, and then for each relation, so I draw these vectors from this joint distribution, and for each relation of the vector, I draw a convex hull. I choose another sample, I get another convex hull. And so the convex hull, therefore, is a random object given this joint distribution. And the main problem is, what can we say about the statistics of the convex hull given this joint distribution? Okay, so that's a very general problem. And in particular, observables. A simple observable is the perimeter, for example. So if I look at the perimeter of the convex hull, the perimeter also changes from one sample to another sample. What is the mean perimeter, for instance, or the distribution of the perimeter? Similarly, you can ask for the area of this convex hull, or even the number of vertices. For example, some vertices are on the convex hull, like here is 4, here is 3. So that number is also changing. And so that's also a random variable. So that's a generic problem. Okay? So given this P, what can we say about the perimeter or the area or this kind of things of the convex hull, statistics of convex hulls? Okay. So that's the question. And now there is one case which have been studied quite a lot in maths literature, which is when this joint distribution factorizes. Okay, so this is a factor, that means these are points, IID points, independent and identically distributed. This can be Gaussian or uniform or whatever distribution you want. And this problem and the associated convex hull problem, the statistics of convex hull. So this has been studied by diverse methods, starting from Levy in 1948, and still people are writing, papers on this independent variable problem. And but the thing is that there is no unique method. It depends on the particular distribution. Each distribution, people try different methods and to compute the statistics of the convex hulls. Okay. Now the problem that I'm interested in here, and I'll come to that in a minute, the motivation for that is when these points are not independent, but they are correlated. Okay? So in that case, there is essentially no general method to solve this problem. So the simplest example of a correlated points is a random walk. So imagine that you have a random walk in 2 dimensions. It starts from the origin. It's occurring in discrete time, but eventually I'll take the continuous time limit. So, for a random walk, X component and Y component, each of them evolve independently. So at each step, it's a Markov process. At each step, it just draws a random increment or jump, and it jumps. Okay, so then the walker is moving like this. So this is an example of 8-step walk. And these are just noises drawn from some distribution. And in the limit, when you take the continuous time limit, so that means you get a Brownian path of duration capital T, let's say. So in that case, these equations here, they just becomes just the Langemann equation dx d tau equal to noise, and these noises are just uncorrelated white noise, and d is the diffusion constant of the Brownian motion. So given this random walk, and now why is it a correlated point? Because in the random walk case, even though the noise or the increments, they are uncorrelated, but since x and y, they are sum of noises, so they actually get correlated. So these points themselves are correlated. Joint distribution doesn't factorize. And so in that case, you can ask, what can we say about the convex hull of a Brownian motion? Okay. So I take a Brownian motion of, this is I draw this just for a discrete work so that we can visualize it. But you will think you can of course study the discrete problem also, but it's easier to look at the continuous time limit. So again, I should draw one particular sample of the history of the random walk trajectory, and I draw the convex hull. Okay, and then I look at another trajectory. I draw the convex hull. So the convex hull is changing from one trajectory to another, and you want to know that what can you say? For example, the simplest question is what can you say about the mean perimeter or the mean area associated to the convex hull? Okay? But just a single Brownian motion. And again, this problem, has been studied somewhat, for the last 40 years or something. And what is known, for example, the mean, perimeter of the convex hull. So this is known as square root of 2 dt. Now, time dependence here is a kind of trivial scale because it's a diffusion. So obviously, the length scale is only square root of dt. Okay, so that's not very interesting. But this is what you'd expect, dimensionally. But what is interesting was to compute this prefactor here, root 8 pi, which was highly non-trivial, and this was computed by Letak and then Takashi in the 1980s. And then the mean area is also known. Again, area, scaling wise, it will be just 2 dt times some constant, and this constant pi by 2 was pretty non-trivial to compute. And now you can ask the same question. In some applications, what you have is not just a free Brownian motion, but a Brownian bridge. By Brownian bridge, I mean that you retain only those configurations where after a fixed amount of time, the particle comes back to the origin. Okay. So for the Brownian bridge of duration t, starting at the origin and returning to the origin, again, you can look at the convex hull of different relations, and you can ask what is the mean perimeter. So again, mean perimeter, as you would expect, time dependence is trivial, as I say, but this coefficient here was root pi cubed over 2, which was computed by Goldman, and by quite complicated method, and it was non-trivial to, and the mean area was not even known when we started working on this problem. Okay. So this was the sort of main motivation to see what's as a physicist, how do we actually even approach this problem? Okay. And then what happened was that about 2009 or something, I was visiting Luca in Bristol, and he actually posed this question. He said, okay, this is the trajectory of a single Brownian motion. Okay. You draw the convex hull. But in many applications in ecology, people actually are interested in what is called the home range for animal movement. Home range roughly means the territory over which the animal moves. And typically they're estimated by this convex hull. Okay, you take the trajectory, like you put a GPS on an animal, and you get the trajectory, and then you just draw the convex hull, and that gives you roughly the area over which the animal moves. Okay. Now, if you want to construct, for example, a reserve forest for animals, you want to reserve some area for the forest. So then, of course, you have not one animal, but many animals. Okay. So here is just 2 Brownian motions, for example. And so the question was that, how big is the home range? If you have n animals, let's say you have 10,000 tigers or something, so how big should your reserve forest be? Okay, so which means that how much area you should need to reserve for the home range, and so therefore it's important to know that if I have n particles, okay, each of them is doing some motion, and they may be independent or correlated. Of course, when they're correlated, is very difficult to solve. But let's say even for simple n Brownian motions, okay, so n tigers, if you like, and I want to look at the convex hull, and time dependence is not important here. It's just the size of the population. So you would expect, of course, when you have n animals, the size of this convex hull will grow with n. And how do you know? How can we estimate how it grows? How it depends on the sample size. So that was the sort of problem. So more precisely, so what we have right now is that, so this is the convex hull of one single Brownian motion, or one single random walk, if you like. Now the point is that if I add one more random walk, so this is the purple color here, and the black is the first one, so 2 walkers. So you see the convex hull, it's not just an additive functional. It's not just, they just add up the convex hull. The convex hull changes very non-locally, right? So because now the convex hull will be the union of the, 2 trajectories, and their convex hull. So it's not completely clear that how does it depend on the size as you increase. If you have n random walkers, how does the convex hull area or the perimeter behave with the sample size n, number of animals n? Okay. So that's the question I want to address. That is, what's the mean perimeter ln and mean area an of n independent Brownian paths or Brownian bridges, if you like, each of duration t. So again, the time dependence is quite trivial. It will be always square root of dt because of diffusion. But I want to know the dependence on n. the animal population basically. How does it grow? And I remind you, so what you would expect, as I said, the average perimeter will grow like square root of 2 dt, and average area will go like 2 dt. But these coefficients, alpha n and beta n, they depend on the number of animals. And problem I want to address is how do they depend on n? Okay? And I remind you that for n equal to 1 walker, the known results for the open path, it was square root of 8 pi and pi by 2, these two coefficients. And for the closed path, this was square root of pi cube over 2, and beta 1 was not known. All right, so that's the problem. Okay? So I want to know the n dependence of alpha n and beta n. So in particular, you can do the simulation very quickly. And what you find, this is, for example, the picture for n equal to 3 closed paths, and this is n equal to 10 open paths. So, I mean, as you see, obviously you would expect it will grow with n. Okay? Question is, how does it grow? Anybody wants to guess how does it grow with n? We'll see. Does it grow linearly or square root, whatever? I mean, okay, we'll see. So this is the problem. So I mean, I hope the problem is clear to everybody, right? So this is the first problem I want to address. And the second problem is actually this epidemic problem. So this is actually in Australia. So there is often the horse population there. They have this influenza epidemic. And so basically a horse gets infected, and then it sort of moves around, diffuses, and it infects other horses. And so what they do is they look at the farms where there is epidemic, and they actually use the convex sun. So the area which is infected, they estimate it by the minimum convex sun, and to see how the epidemic progresses for every 2 days. Okay, so a simple model that you can think of is actually branching Brownian motion. So I'll explain to you what I mean by that. So imagine that you start with one horse here. So this horse is just diffusing, and at some point it infects another horse. So what I'm plotting here is only the infected guys. Okay. So now it infects another guy. So now we have 2 infected guys. And then each of them it may infect another guy. So we have 2 more. I mean, here, the original guy and the new guy, and so on. And once in a while, somebody will recover. And recover means in this language, I mean, it's dead, meaning that it's dead from the picture, basically, it recovers. So the simplest model you can think of is a continuous time model, is like a branching Brownian motion. So you say that you start from the origin, a Brownian motion, and then with rate b, that means in a small time dt with probability b delta t, it infects another person, that means it branches into 2. With rate a delta t, it recovers, that means it just recovers, that means it dies, if you like, death. And with the complementary probability 1 minus b plus a delta t, it just diffuses. Okay? So that's the simplest model. Yeah.
But infection is a 2-body interaction. You need another horse to be there.
No. So there are horses, but you're not. I mean, this guy, each person is moving basically. Each person is moving and infecting another person basically.
You start with the horses are independent.
No, horses are there. Horses are there. And the infected guy, it starts with one guy who is infected, and this guy goes and infects another person. And that guy goes also, and this guy goes and infects another person. So it's like the branching process. And once in a while they recover or they die or whatever, which is the.
But as the number of infected grows,
yeah,
the rate decreases because the number of available.
Yeah, so you can assume that there's an infinite population. I mean, that's in branching Brownian motion, that's a basic assumption that you have an infinite population. Okay, so that it doesn't depend on, so it's just for simplicity. And so basically this is the picture after day 2, and it grows, and day 3 it grows, and so on. And so now what happens here is that when the infection rate is bigger than the recovery rate, then of course you'd expect that the epidemic to explode, and it does. And on the other hand, if B is less than A, then the epidemic becomes extinct after some time. And the critical case is when B equal to A, then the epidemic sort of sustains for a very long time, and it doesn't explode, but it has this it's called a critical epidemic. And this is exactly what happens in fission, nuclear fission. Okay. this is precisely what happens. I mean, when people do the experiments in the lab, you don't want, they are interested in the critical case because you don't want supercritical, because then everything in the lab will explode completely. And you don't want, the number of fissions to become extinct. And so the critical thing is what the nuclear physicists are interested in. Okay? And so here, so again, if you draw the convex hull, you want to know here, the important question is how does it grow with time? For different cases, I mean, supercritical, subcritical, or critical. And we'll be mostly interested in critical case. Okay. So the question is then, how does the perimeter and the area of the convex hull of this branching process grow? How does it grow with time t? Okay. Here the dependence on t is important. All right. So there are two problems that I discussed. So let me summarize. So first problem is that you just look at the simplest problem is that n independent Brownian motions, each of duration t. Here the t is not very important, it just scales out. And we want to, get the home range estimate and the dependence on the population size n. And the second problem is this branching Brownian motion with death or recovery, if you like. And this is a model for animal epidemics, simple model. And here we want to know how does the perimeter and area of the convex hull grow with time t. So the problems are very well defined. I mean, you can do simulations very easily. And but we wanted to make some analytical computation. Okay? So yeah.
So the perimeter, the area of the parameter you are interested in. Do you know if there's something is known about the diameter, the maximum distance?
So people study diameter also,
okay.
And but it's actually much more harder to compute. Even this is very difficult to compute. So there are some cases you can just calculate the diameter, but even for a Brownian motion, diameter is not known. Okay. So the question is that okay, if you want to make some progress with the analytical computation, how do you proceed? I mean, the problem is very well defined. We are stuck. So how do you? What's the starting point, right? So at this point, so what do? You go back and look at the old literature, and so while doing that, we actually came across some very old paper by Cauchy from 1832, and this paper is really amazing. Okay, I wrote down here. So he actually, his motivation was completely different, but here's the question. I mean, we all know the formula for the area and the perimeter of a circle. Right? If I give you any another convex curve like ellipse, what's the formula? Ellipse actually can work it out. Yes. But if I give you any closed convex curve, is there any formula, simple formula for the perimeter of the area of such a curve?
Or triangles.
Or triangles, for example. Okay.
Yeah.
Yes, exactly. That's where I come. So Cauchy actually, so he actually had this answer to this question. Okay. So here is Cauchy's formula. So if you take any closed convex curve, so first thing you have to define is what is called the support function. So what is the support function? The support function is just you take any direction theta. Okay, and let's say you take a stick perpendicular to this direction, and you bring the stick, and when you touch this guy, you stop. And then you just look at the distance from the origin to that stick there, perpendicular distance. So that is called the aim of theta. Okay. So formally, mathematically, it just says that if I take xs and ys are any point on this closed convex curve, I look at their projection in the direction of theta, and I take because each point has a projection, and I take the maximum of those points. Okay. So that is the end theta. But geometrically, it's actually like this stick example is very easy to visualize. All right. So if you know this m theta, then the Cauchy's formula says that the perimeter of any closed convex curve is actually integral of m theta d theta. This is sort of well known. You can find in the literature once in a while. But even this formula, the area formula, is not at all well known, and but it was there in this paper. Okay. So this is the paper from 1832. So this is m square of theta, and this is dm d theta, derivative of m theta with respect to theta. And of course, Cauchy's paper, there's 2-page letter in French for the academic exams. and it was not easy to understand. But once you know the formula, you can cook up a physicist proof. So let me just show you this proof. So this will be useful for us. So what's the proof? So we go by physicists. So essentially you have a closed convex curve. First you approximate it by polygon, and you take the vertices of the polygon you take to be very, very large, so that finally it approaches the convex curve. Okay. So let's look at this polygon. And now I just zoom in some corner here, this corner A, and I'm just looking at this in a zoomed way. I take any arbitrary point A inside, doesn't matter where the origin is. I draw this line here. So suppose this distance is R, and I just, this is a very simple trigonometry proof. I just, draw the perpendicular, and suppose that this angle is phi1 and this angle is phi2. Okay. So then you see immediately, and what is support function? Again, if I bring my stick, I stop here because I just touch this point, right? So therefore the M is this distance here. So what is the M? M is just R cosine theta. And for all these points here locally, R doesn't change. R is same for all these points here on this polygon. So M of theta is just R cosine theta. So let's just integrate this guy from minus phi1 to phi2. So this gives me R sine phi1 plus sine phi2. But R sine phi1 is just this distance here, and R sine phi2 is just this distance. So this addition is just this length. And you do it for every point here in the polygon, and you close this curve, and you see that this is the image. And similarly, for the area, so again, you just do M square theta is just R square goes out, and you have cosine square theta, sine square theta. You just do this integral simply, and you get this, and which is again, this is the area of this triangle here, and this is the area of that triangle here, and so therefore this is just the area of this parallel pipe, and then you add them up when you go around this, and that gives you the area. So this is of course for that you need to know this formula, and you can verify, but to prove this is not, I don't know how to prove this. So let's just check some simple things. So for circle of course it works. Circle centered at the origin. M of theta is just R essentially, because it doesn't depend on theta, so it's just R. If you plug it in, you get the familiar formula that you all know. And slightly non-trivial is if you take the circle, but now you choose your coordinate O to be at this point here, and then you see that the M theta is actually R times 1 plus sine theta. But again, if you just put it in here, you get back as it should be. This formula is independent of the topology of this thing. It doesn't matter where you choose this origin. So these are in some that sense topological formulas. Okay. So this is a nice formula. And the main point is that this formula actually holds for any closed convex curve. Any closed convex curve. Okay. And this is the key to what I'm going to tell you now, because the idea we had was to just apply it now to random convex curve, basically. Okay. So how do we proceed? So it's the idea is essentially very simple. So you can take any stochastic process in 2D, let's say starting at the origin. Okay. I'm just drawing it like a random walk, but it can be any process. Okay. And suppose that little xk, yk, these are the vertices of this, let's say, in state walk. Okay. And let's suppose that, so given this trajectory, I have to draw the convex hull, which is shown by this green dotted line. Okay. And so Cauchy's formula, then I can apply to this convex hull, okay, the green curve. But then it looks like a very difficult problem, right? Because you want to calculate this formula here for M theta, but for M theta, which is the projection of this, x cosine theta plus y is sine theta. But for that, you need to first know the equation of this convex hull, which looks very difficult, right? So it's not so easy to apply this formula there. How do I actually first calculate x's, y's, and then I have to take the maximum? But the key point, and this is the crucial point, key point is to realize that this is the object you want to calculate, right? Support function. for this convex hull. But then you realize that if I know the coordinates of each of the vertex of the underlying stochastic process, then this object just requires a little bit of thought. What you can show is that this is exactly same as xk cosine theta yk sin theta, because this is the m theta is just the maximum projection of the convex hull in that direction. But then this convex hull must have a point where you stopped, right? That's a vertex. So that's a projection of that vertex. So essentially, if you can keep track of the vertices of your walk, that's enough to tell you what is m theta. I don't have to actually draw the convex hull first and then calculate that of the convex hull. I mean, it's enough if I just keep track of the the vertices of the underlying process. Okay. And in particular, as I said, there will be one point k star and y k star, which is for a given theta. That's the object you stop there. So it's x coordinate and y coordinate, x k star cosine theta, y k star sin theta. That's your m theta. So k star is the level of the point with the largest projection of theta. And this is the crucial thing. Once you get this, then the rest is just kind of straightforward. Okay. So once you have that, then it has a nice physical interpretation. So m theta is this distance, and m prime theta, which I need for the area formula, is just the perpendicular distance of that. Okay. All right. So once you have that, so the idea is, and the point is that the Cauchy's formula, I mean, since this formula holds for every possible convex curve, so I can actually take an average here. Okay. If I take an average, so that will be the average of m of theta, and similarly, average area here will be average of these objects. Okay. And this m theta is therefore just x post k star cosine theta and y k star sin theta. So geometrically you can see this. This is the m theta, this is the m prime theta, and I just have to complete these objects. Yeah.
This is an ensemble average, right?
This is an ensemble average, yes.
Do a lot of realizations for each random walk.
Exactly. Now, you can use for Brownian motion or random walk. I mean, you have one additional property, which is the isotropy, that the joint distribution of these points, if I make a rotation, it's invariant under the rotation, right? So therefore, the integral 2 pi m theta d theta just becomes 2 pi expectation value of m of 0, theta equal to 0. But theta equal to 0, you see, this is just the maximum of the x coordinates, right? So essentially, you have reduced this problem to a one-dimensional problem. Okay? You want to know the maximum of the projection of the x coordinates. Okay? And for the area, we need the variance of the maximum of the one-dimensional process. And then there's this object here, which is the y coordinate at the time when x achieves the maximum. Okay. So effectively, what happens here is this is the link to the extreme value statistics. The extreme value statistics usually refers to a one-dimensional process, and you want to look at the distributional statistics of the maximum. So this is the link to the extreme value statistics. So all right. So then what we have then, so now I go to the continuous limit. So I have a Brownian motion of duration t, and x tau and y tau are the coordinates of the Brownian motion. So then the mean perimeter is just 2 pi times the expected value of m of 0, and m of 0 is just the expected maximum of a one-dimensional Brownian motion. And for the area, I need the variance of, I need the second moment of that, and I also need that the y at the time when x is maximum. Okay. So this is the, so here is the process basically. So essentially you have, look at the x component is doing something, and you look at the time at which it achieves the maximum. So that's your aim of m0. Okay. And you look at also at the same time, you look at y tau versus tau, and you have to look for this guy here. What you need is m prime of 0, which means that the y at the same time at which x achieves its maximum. Okay? Because tau star is the time at which x achieves its maximum, and you want the y exactly at that time. So m prime 0 square average, which is the second term here, So essentially, this is the y square average at time tau star. And for diffusive process, y is doing, Brownian motion by itself. So this is just a 2D times the expected time at which the maximum occurs for the one-dimensional process. Okay. So essentially, what happens is that therefore it reduces for any isotropic, stochastic process like which is in case of diffusive. If it's not diffusive, you will have to calculate this a little bit more complicated. But for diffusive process, so the mean perimeter is just 2 pi times the expected maximum of your one-dimensional Brownian motion, and the mean area is just the second moment minus 2d times the expected time of the maximum at which the maximum occurs within any window of size capital. So this is a sort of very nice result, and now let me just see what it gives for different cases. This general formula. So let's think of a single Brownian path first. So what I need is the joint statistics of the maximum of the one-dimensional Brownian motion and the time at which the maximum occurs. Okay. So this is actually very easy to compute. So the subscript 1 means 1 occur. And this is very easy to compute. You can just use quantitative method. I'm not going into the details. But the joint distribution of the time of the maximum and the maximum is given by this. And I just said d equal to half for simplicity. And so from this, you can compute easily the expected maximum, which is square root of 2t by pi. You need m square, which is t, and you need tau star, which is t by 2. And if you plug it in this formula that we had, so you recover the result, the square root of 8 pi t, which I had told you before, which was derived by Takahashi and company by a very different method. And for the mean area, you get back the pi t by 2. So this was just a check. Okay. And for the bridge, mean perimeter, we recover again this formula by Goldman. Okay. And for the mean area, we get pi t over 3, which is the new result. This was not known before in the maths literature. Okay, so this was just for a single Brownian motion. Now, if I go for n independent Brownian motion, it's exactly the same, because all you have to do now is will be just 2 pi times expected mn. So expected mn means that you have n independent one-dimensional Brownian motion, and you want to know the the expected maximum of that. Okay. And similarly here, exactly similar formulas. Okay. So how do I calculate that? So if I have n independent Brownian motion one-dimensional, and I want to know the statistics of the maximum m and the time at which the maximum occurs. So basically, then the idea is very simple, because since they are independent, and that's why I'm using the independence of the occurs. So you have to make sure that let's say this one guy achieves its maximum, number one. So what's the probability that its value is n and the time at which its maximum occurs is tau star? Okay. So this answer we have already seen before. And now I have to ensure that all the other guys, they actually stay below the level n, right? And this is again, it's a survival probability you can calculate very easily. So this is just our function n by p to the power n minus 1. And there's a factor n here, because the maximum can be achieved by any one of the n occurs. So this is a simple formula. And so all you have to do is to calculate the expectation value of m square, and the y, tau star. So now I just flash the result and show you what happens. So I just have to calculate this object. So you know the joint distribution. From this, you just calculate the expectation value of m and m square and so on. Okay. So now I'll just show you this as a result. So what you get is ln, expected perimeter, actually goes like alpha n by root times, I said diffusion constant to be half, square root of t. As I said, square root of t is not very important here. And alpha n has this formula here. This is exact. And you can check alpha 1 is this, alpha 2 is that, alpha 3 is that, and so on. Okay. I'll come to the asymptotics in a minute. You go to mean area, again, you can, knowing all the phenomenology is there, so all the formalism is there, you can calculate, and this is a little bit more complicated formula, yeah. But it's an exact formula, you can compute for all values of n. And now you go to, for closed paths, okay, the bridge. So for closed paths, again, this alpha n c times square root of t, alpha n c you can compute explicitly, and with values, and similarly for the area, they are a little more complicated, but they're explicit results basically. All right. So and then you can plot. do simulations and you can plot. Okay, these are open paths and closed paths for area and the perimeter. I don't know which one is what, but it matches very well in the predictions. All right, so what is asymptotics? So what you find is that for n open paths, okay, so n is the animal population size. The mean perimeter actually goes like square root of log n. So it grows, but it grows extremely slowly. Okay. And the area goes like log n. And for the closed paths, it's similar, except with factor 2, which is different, and here is factor 4, square root of log n and log n. And as n goes to infinity, the convex hull, when you have large number of animals, the convex hull actually approaches a circle. Because if you calculate the area divided by perimeter squared, it becomes 1 over 4 pi, which is the isoperimetric bound, and it approaches a circle. And so nice thing is that if you say that, okay, if I have any animals, so I have to reserve an area for the reserve forest. So it says it actually grows very, very slowly, which means which is a good news because I don't have to reserve very big area, right? So if I have 10,000 tigers, I mean, it will be 1 kilometer. I don't know, but okay. But this of course ignores all the interactions between the animals. But okay, with short range interaction, this is still robust. I mean, it still goes like log n. So this was the sort of. In retrospect, it's not that. Once you know the connection to extreme value statistics, because you can see that where this square root of log n comes, because if you have n Gaussian variables in one dimension, the maximum actually goes like square root of log n. So from there, this is the explanation for log n. Okay? So essentially, the conclusion is a very slow growth of the home range with population size. So now I come to the second problem, which is the animal epidemics. And again, the result is very similar. So, and I just show you the result only for the critical case, because what happens when the B is bigger than A, when there is a supercritical phase, then you have the traveling front solution as in the Fisher equation, because when you look at the statistics of the maximum of one component, that means one-dimensional Brownian branching Brownian motion, and then if B is bigger than A, then you have a traveling front maximum goes linearly with T, and this is the Fisher equation essentially, it's well known. But in the critical case, when B equal to A, then of course it goes to a steady state, the distribution of the maximum. And so from this we can work out all these results. I'm not showing you the details. So what you find is that the mean perimeter actually goes to a constant in the large T limit, okay, at the critical case. Okay. It goes to a constant, but the mean area keeps on growing slowly as log T. Okay. So this was a joint work with Brownian and Andrea Zoya and Alberto Rosso. And so this is sort of interesting thing that the perimeter actually, you might think that perimeter goes to a constant, but area still keeps growing. How is that? And to get to that, so what you find is you can actually look at the distribution of the perimeter, and you can argue that the perimeter distribution in the long time limit actually has a power law chain as n to the power -3. Okay. So the mean perimeter, if you take the first moment of that, it's a finite convergent integral, so it's finite. But the area actually has a power law chain, which is a to the power -2. Because if, roughly speaking, area is like L squared. So if PL goes like L to the power -3, PA therefore goes like A to the power -2. And you see the mean area in the long time limit is actually divergent. And that's what you see here, that if you're looking at a finite but large time t, this keeps on growing and finally diverges, whereas this goes to a constant. Okay. And the reason for that is because the distributions have different power law tails for the perimeter and the area. And this is the numerical verification of that. Okay. So let me summarize just this part and then I'll just come to more recent stuff. So essentially what we have is an unified approach, using this Cauchy's formula to calculate the mean perimeter and area of the convex hull. And in fact, this is also even for when the points are independent, not Brownian motion, but if the points are independent, for which there's a huge mathematics literature. But they were all using different approaches for different distributions. But with this, at least for the mean perimeter and area, you can actually, using the Cauchy approach, you can get all the results that were known in the literature. And also it provides a nice link to this extreme value statistics, which is another subject area in which I'm interested, and many other important work is being done now. So that's a nice example of extreme value statistics. And for planar plots, you have open and closed, you have exact results. And the ecological implication is that this home range estimate is that it's a very slow growth of the home range with population size. And for the branching Brownian motion of death, you can apply it to the spread of animal epidemics. And again, area grows very slowly as log T. So let me just, last for 10 minutes. I just want to talk about more recent stuff. This was a little bit older. So, now that we have this formalism, we can actually apply it to other processes. So the most, recent thing that we looked at is the run-and-tumble particle. Just to remind you, those of you who don't know, Brownian motion, as you know, so it's like a particle immersed in a fluid, and this particle has no autonomous motion on its own. It moves because the other fluid particles come and bombard it from all directions. So then it just diffuses. So this is the good old classic Brownian motion. Whereas in active particles, what happens is that it, like bacteria, it absorbs energy directly from the environment, and then it sort of chooses the direction at random by tuning its flagellar tail, and it moves ballistically. It's a self-propelled motion, so it moves ballistically in that direction up to a sort of exponentially distributed time with a time scale which is called persistence time, essentially. Okay, so in tumbling rate. At the end of this random time, it stops, and then it sort of chooses another direction at random by reorienting the flagella, and again moves up to a exponentially distributed time, and then again tumbles. So it's called run and tumble particles. And so essentially this V0 is the speed, and the gamma is the tumbling rate. And it chooses the, here I'm talking about isotropic direction, essentially. And so here you can ask the same question. So suppose I have this E. coli bacteria, and I look at its trajectory, and I ask, what can I say about the convex hull? How does the convex hull grow with time? So this problem, is again, we can apply the same. So we want to calculate the perimeter, for example, of the RTP, the run-and-tumble particle of duration T. And so we can again map to the one-dimensional component process, and I'm not showing you the details. And you can calculate, you can find an exact formula for this mean perimeter. So this is given by some scaling function of gamma T, dimensionless time. And this function H, you can write in terms of special functions, Bessel functions, true function, whatever. And so here is the simulation results. You see that it works very well. And it has this following behavior. If the capital time, the duration, is much less than the persistence time, then it goes linearly. You will expect that it goes ballistically. And on the other hand, if time is much bigger than gamma inverse, then of course it goes diffusively at very late times. That's what you would expect. And you get the precise behavior of this the long time limit, for all time actually. What about the area? So the area is actually much more difficult computation, and this was very recent calculation that we did in the Anupam is here. And so we found that this is a scaling function again of gamma T, and this scaling function is very complicated. I don't want to write down the slide. But nicely, interestingly, what you find that the mean area actually has also, the two types of asymptotic behavior. When time is much less than the persistent time, it actually goes like T cubed. So which is very small actually, because it's small T essentially. And for large T, it goes diffusively, as you would expect. But this T cube behavior, it happens because, at early time, essentially you have just one tumble. So just one tumble and this, and then you want the convex hull of this. The convex hull is actually a triangle. And for the triangle, if you calculate the area, so this would, you can show that this would actually go like T cube. So that's quite nice actually. And all right, so this is this RTP process. And the other process we looked at recently was resetting Brownian motion. So resetting Brownian motion means, you take a Brownian motion, and with rate R, you go back to the origin, okay, so, and then restart the process. Okay, so this has been, has been studied quite a lot in the recent literature, in the search phenomena and so on. And you can ask, if I take a receding Brownian motion in 2D, what can I say? So these different colors here represent the process after resetting. So, initially it was going like this green color. After one reset, then it goes with the orange color and so on and so forth. Okay. And so again, you can use the same methodology. So all you have to do is so the resetting Brownian motion precise model is the following. So with probability R d tau in a small time d tau, you go back to the origin. So this is the resetting move. And with the complementary probability, you just diffuse, okay, add random noises basically. So this was the model which introduced with Martin Evans, about 10 years back, and now it has been used many different search contexts and so on. But you can just ask, what is the convex hull of this process, search process? Okay. So there's a recent review on stochastic resetting and applications with Evans and Gregory Sher. So here again, we can calculate the mean perimeter and mean area. I'm not showing you the calculation details, but just to say that again, you can write down as two scaling functions, f1 of RT and f2 of RT. And these functions you can compute it explicitly. Okay, these are just horrible functions, but basically what it does is that what you can show is that because what resetting does is not letting the system grow, because it's resetting or going back. So the growth problem is a growth problem, but it's a sort of limited growth. And even though the system actually goes to a steady state, but the convex hull actually still grows. And in fact, it grows like mean perimeter goes like log t, and the mean area goes like log square of t. And again, slow logarithmic growth of the convex hull. And this dimensionless ratio, it goes to 1/4 pi, which means that the convex hull actually becomes a circle at the long time limit. Okay. So then there are other processes. I don't want to bore you with the details, but many different problems like 2DR, Gauss polymer chain. But essentially the method is always similar, that is map to the one-dimensional problem and solve the extreme value statistics of one-dimensional problem. So let me just finish by
Sorry,
yeah.
Did you look at the problem when they're not independent?
Yeah, so this is yeah. If you have interactions, then it says, it's the only problem is that then the associated one-dimensional process also becomes very hard. So you can do it numerically, but analytically it's very hard to do anything. Okay. So, but I'm saying that even when there's no non-interacting case, the convex hull is actually because it's a nonlinear functional of the trajectories of each particles. So even for the independent particles, it's very hard to compute. And right. So you can actually ask for the discrete time random walk. So so far I was talking about Brownian motion, continuous time, but discrete time also we can work it out explicitly. So there have been some results here, and but the main interesting thing is that you can say that the only the drawback of this approach is that I can calculate the mean perimeter and mean area, but even to calculate the variance, the variance of the perimeter or the variance of the area, even for a single Brownian motion, this is not known. It was very hard because you see that if you want to calculate the L square here and take the average, so then you need to m theta1 and theta2 correlated, and this is a very complicated problem in the cone two-dimensional thing. Okay, so it's not so easy to compute. Okay. So our distribution is even harder, of course. And so those are open questions. Only numerical results are available, and more recently, the people are maths literature people are looking at the large deviation tail of these distributions of the perimeter area, and then you could ask, what happens in higher dimensions? Higher dimensions are analog with the convex polytope, not a convex hull. And for a single Brownian motion, there is some exact result by mathematicians here, and but by using very different methods, and but nothing is known for for n particles, so that's an open problem. And this is exactly what we're asking: effect of interaction between the convex. There's essentially no work that I know of, not yet. Okay. But it's a very interesting question, of course. And then you can ask, non-Brownian paths like, self-evident walks and things like that. Again, for self-evident walk, it's very hard to calculate because corresponding one-dimensional process is a very complicated process with the memory, non-trivial, memory kernel and so on. So it's again mostly numerical results and not really, no analytical results. So let me just thank my collaborators. So I started this work with our company with my colleague at OSE, and then there were several students who worked on it, and also with regulation and William from Saclay, and I got to from our lab, and there are the people who is here, and his student Prashant Singh, and so on. So that's it. Thank you very much for it.
Do you think this can be generalized to continuous time random walkers?
Ah,
Those who have
yes.
long waiting times?
Yes. So in fact, this has been done for continuous time random walk. If I remember, by Stefan Weil and somebody else, they had looked at, they used exactly similar method as this approach. And for continuous time with the given waiting time distribution, you can actually compute this.
And then so these probably.
Yeah, there it becomes more important, much more. Yes, absolutely. That's true. Yeah.
So you mentioned some results about the Ross coordinate.
Yes.
So they also calculated the area
Yes.
in dimension 2 also.
Dimension 2. Yeah.
Okay, dimension 3 is
Still okay.
because this would be very important in
Sure.
the case of the
Of
nucleus.
course. Yeah, dimension 3, I have no idea how to proceed this.
Because obviously this relies fundamentally on
Yeah.
dimension 2.
No, of course. This is no, in fact, I don't even know what is the formula for a convex polytope. There is no formula as I know, analog of Cauchy's formula. So this is a very interesting question.
And there are results also, for example, for Orshad processes instead of Brownian motion.
Yes, so with process you can actually calculate because you can calculate again the maximum. So this was actually because this was, let me see if I have this. We had this was actually this is random acceleration. Yeah, so this was a work that we did with Olivier Benichu and his students, and so here we needed the Orshad process actually. So this problem was like if you have a reflecting wall, for example, in 2 dimension, but suppose that you have a reflecting Brownian motion with a wall. So it's like you have a reserve forest, but let's say you have a highway, and where the cars are going, so the forest ends there. So the animal goes there and gets reflected with this one. And then you can ask, what is the sort of convex out there? And then it's kind of quite interesting behavior of the perimeter. So the perimeter, depending on this. And while doing this problem, we had to basically solve the Orshad process because all you need, basically for any process for which you can, for the component process, you can calculate its maximum. Then you are done basically. So that's the thing. So Orshad you can calculate the expected maximum, so you can actually calculate the whole thing. So,
And you said diameters, you look at the maximum distance, you cannot of course use.
No, diameter is diameter basically what people call caliper diameter basically. So you have a convex arm, and you look at take this, and for every direction you calculate the caliper diameter. How close can you get, and then you look at the maximum of that. That is usually defined as diameter. And for that measure, very few results are known actually. One doesn't even know, how to approach this problem. Yeah.
Your habitat has hills and valleys. Is there a generalization of these Cauchy results for the error monitor?
That's an interesting question. Yeah. Yeah, if you have hills and valleys, of course, you look at the projection in 2D, but in 3D, again, how to take into account the dimension 3, I don't know. I don't know of any particular formula or something or the other. But what I expect is that if you have hills and valleys, then of course what can happen is that if you have a Walker, I mean, this diffusion constant will probably vary from one place to another place, the hill or something, right? Diffuse slowly compared to other things. So you can actually ask that, okay, I mean, you can ask this question that if I take a Brownian motion, but the diffusion constant that depends on space, for example. And what can I say about the convex hull of that? That's true. Yeah. So that's an interesting problem actually. I mean, I don't think anybody has addressed that question. That when the diffusion constant, is a function of space. So that would be interesting to look at. I mean, that will roughly be closest to what you're asking in some sense. I mean, if I say that okay, some places it's harder to move and some places it moves quickly. I mean, that's an interesting problem to ask. How does that reflect on the statistics of the convex? Yeah.
I think from Luca, I remember the problem that there are animals in the plane and then different nests. So they start at different initial conditions.
Right.
And then they have a home range. And then one may ask the question, okay, what's the home range of if you have different initial conditions and that's also the overlap? I think that was also likely simple scaling.
Yes.
I don't know, but I mean,
no, true, but you can apply this phenomenology there also. It's just a more complicated problem. But essentially, you can apply even if they have different starting points.
Yeah.
These guys, I mean, you can still, still do this analysis basically.
has this been done?
Not that I know of. Not that I know of.
Right, your question.
Yeah.
So, who read the paper preventing veterinary medicine? Who actually got that?
I just,
You managed to find, I mean, just because.
yeah, I mean, you just do a Google search, you'll find it.
True.
But true, I mean, I just, we just found it by accident in some sense. I mean, always, I mean, no, actually, a miracle happens, right? When you are looking for, especially when you are looking for something, thinking about something, you somehow always come across, papers and exactly at that time dealing with such things, right? So it's always happens. So, yeah. So this is the paper. Yeah.
Veterinary medicine.
Yeah. So yeah. So.
Question? Okay, let's thank Satya again.